Alright, so in the last video we stopped at the formula for the um, multivariate Newton's method. So in this case we're looking at z is equal to f of x, or y equals f of x, where f is mapping Rn to R. And then what this is actually doing is it's finding the zeros of the gradient of f, right? And so that's why you have the second derivatives appearing here. So this is actually the first derivative and the second derivative. Okay, so this is also the inversion of an n by n matrix. And so we may run into trouble with that. The implementation of this is pretty straightforward. To implement this on the computer, basically what you need is just a function that inputs x and outputs. I would have it output f of x as well. F of x, that's a scalar. And then your gradient of f, that's a vector. And then your Hessian of f, which is your matrix. Okay. And then you just plug those into your formula and just start iterating. So you might run into trouble with the matrix inversion depending on how many variables you have. And there's of course other issues, right, with Newton's method. Newton's method works the best when it's within, a very short, within epsilon, we could say, of the of your solution. And actually, it's you want your function to be convex in a region about your minimum as well. So you don't want to accidentally hit a max, for example. But you shouldn't. So I was just taking a look here. I think one thing you can do is, while we're talking about the implementation, is when you're computing the Hessian, we can check its condition number, or check how invertible it is. And by that, we mean the condition number. So this is something called the condition number of the matrix. And in our case, it's straightforward to compute. The condition number, we usually call it K or kappa, is the absolute value of lambda max divided by the absolute value of lambda min. And I say this is going to be straightforward to compute. Why? Because of course you remember that the Hessian is a special form. Yes, it is symmetric. And so your eigenvalue, you get a full set of eigenvalues, and they are real. And so notice what happens as your minimum lambda goes to 0. The condition number blows up. Of course, that's unless your lambda max is also going to 0. Hopefully that's not happening. Otherwise you could run into lots of trouble. So what people will do is they'll say that, if the condition number is too big, then throw an error in your code so you're not continuing. Because sometimes that can happen. It can get more and more singular as the iterations progress. Good. I think I'm going to stop here a little bit early this time, before we hit the gradient descent, and take a look at a MATLAB Python code. So we'll stop here and we'll resume on the computer. I guess we're on the computer now. You know what I mean.